I think that today's lecture is one of the last lectures because we have next lecture in the end of April and in a week. And in that time, I will give you the problems, a list of problems for examination. And probably we will organize another last lecture in May, about middle of May. We will see. And now I would like to give you topics which we will discuss. Next one or two or maybe three lectures. Today we will finish with derivation of Rosenars-Schneider equation of motion from singular solutions to the Toda, two-dimensional Toda chain. And after that, a few possible ways to follow are possible. Next, we can discuss Toda chain of type B, from which it is possible to derive equations of motion of the deformed Rosenars-Schneider system. Maybe I will give you a few details about it. First of all, what is this Toda chain of type B? Next, we can discuss integrable time discretization of integrable many-body systems like Calogero-Moser or Rosenars-Schneider. This is a rather interesting topic, and there are some open questions related to this topic. And the idea is to define Backlund transformations of these systems. Backlund transformation of integrable model or equation is such transformation that sends solutions to another solutions of the same system. And using this, we can define the time discretization. We can organize these Backlund transformations in a chain. First make one transformation, then another one, and so on. So we get a chain. And each step of this chain can be interpreted as a step of time, of discrete time. So in this way, one can introduce integrable time discretizations of these models. This is the first topic. Another topic is field analogues of these many-body systems. What does it mean? In usual many-body system, we have coordinates as functions of time. They satisfy some equations of motion, second time derivative is equal to something. In field version of these models, the coordinates depend on another variable, which is called space variable. Not only on time, but also in space. So in this interpretation, they are not already coordinates of some particles, but they can be interpreted as some fields, n fields. I runs from 1 to n, fields depending on point in two-dimensional space with coordinates t and x. The Lax equations, which come from these many body systems, become Zakharov-Shabat equations. So there is an extra variable, and instead of Lax representation, we have Zakharov-Shabat representation. In this topic, there are also some open questions and interesting things to discuss. What else? Perhaps we will be restricted in this. And today we will consider singular solutions of the Toda chain and derive equations of motion for their poles. Let me first of all, I will give you some general statement. Consider trigonometric solutions to the two-dimensional Toda lattice, which we discussed in the previous lecture. In trigonometric solutions, we have a constant gamma, and this means that all functions are in space variable are periodic with this period. And tau function for such solutions as function of x, which is 0th time. I remind you that in Toda chain we have 0th time, which is called x, and higher times, and also t-bar times, negative times. And this one, usually it is regarded as integer variable, but for the class of solutions that we discuss, it can be extended to all complex values of x, but if equations in this variable are not differential but difference. So the tau function can be written for trigonometric solutions, can be written in the following form. So this is a polynomial in exponential function of x. In a minute, we will denote this exponential function as w, and this will be wi, root of this. It is a polynomial in w, and with roots wi. The limit gamma to 0 corresponds to rational solutions. In this case, you expand the exponent and keep only the first term, proportional to gamma. In one of the previous lectures, we proved that the correspondence between rational solutions to KP hierarchy and rational Kalodger-Moser system, that it exists on the level of hierarchies. So each time flow in KP corresponds to a higher Hamiltonian flow in Kalodger-Moser. And here, for Rusinat-Schneider, there is also a similar statement. So they put all negative times to 0 for simplicity. Then xi depends on t. This is a whole infinite set of times. And it is possible to show that the flow, Toda flow with time Tm corresponds to the Hamiltonian flow in Rusinat's Schneider with the following Hamiltonian. And L is the Lax matrix for trigonometric Rusinat-Schneider system. Previously, we wrote it as a function of coordinates and velocities, but here we need its expression in terms of momentum. The flows in negative times also correspond to some Rusinat-Schneider Hamiltonian, and it is of the following form. So we should take a negative power of this Lax matrix, and we get a Hamiltonian which corresponds to evolution in times with bar. Proof of this statement is rather long and difficult. There are many technical details which are not obvious. And it is especially difficult to show this proof in the blackboard because it requires long expressions, many technical details. You will find this proof in the written notes of the lectures. They will appear on the site. So now I will show you only the first part of this proof, which is just the derivation of the dynamics of poles with respect to the first time, T1, which we call T. So in this, and we put all bar times equal to 0. Then the tau function is a polynomial in the variable w, which is exponent of 2 gamma x, and wi are exponential functions of xi. And it is also convenient to denote this constant by q. So the idea is to consider wave function and substitute some ansatz for these solutions into the first auxiliary linear equation for the psi function. It looks as follows. And this function v is time derivative of logarithm of ratio of such tau functions. So for the tau function of this form, we get the following expression. Dot is time derivative. And the ansatz for the wave function has the following form. It depends on spectral parameter z. And we expand it as a sum of simple poles at the points wi. This form follows from this equation, substituting some general pole expression with probably higher poles into this equation. You will see that only first order poles are compatible with this equation. So we should substitute this and this into this equation. Bring everything into the left-hand side. And then on the left-hand side we have a rational function of w, which is equal to 0 at infinity, with possible poles in the points wi and q to the minus 1 wi. And these poles are simple. And then one should follow the standard procedure and try to cancel all the poles in the left-hand side. And this gives some overdetermined system of equations for these coefficients. So I will give it, I omit technical details and give the result. And write it in the matrix 4. For this, it is convenient to renormalize the coefficients, multiplying them by wi to the power minus 1/2. And then we have two systems of equations. We have 2n equations for these coefficients. 1/2 of them comes from cancellation of these pools, and another half comes from cancellations of these pools. And they, the resulting conditions can be written in the following form. L is the Lax matrix. C tilde is vector with these components. So this is a column vector. And on the right-hand side, we have x dot, and x is, as usual, matrix with coordinates on the diagonal. Similarly, W capital is has W's on the diagonal. And we have these matrices in the right-hand side. And E is, again, as usual, it is a vector whose all components are equal to 1. And another equation is for time derivative. And M, the matrix M here has a rather complicated form. It has a diagonal part. And off-diagonal part. and another term as I said, this system is overdetermined. To obtain a compatibility condition, we should apply time derivative to the first equation, or first group of equations, and substituting this derivative from the second group of equations, you will get the following condition. This is just the expression which appears, always appears in the Lax equation, and Lax equation means that this is zero. But here it is not zero, at least in the beginning. There is the following additional term. A direct calculation allows one to prove that this combination is equal to some matrix R, which I will write here. R is the following diagonal matrix. And this matrix D plus minus R diagonal matrix of the following form. And the matrix D naught is similar, but without this multiplier Q here and here. So the it is just without this. And again, a direct calculation shows that this combination is equal to the same matrix R times x dot times E. From this, you can see that the compatibility is guaranteed if this matrix R is identically zero. However, it is a diagonal matrix, so each diagonal element should be 0. So we look here and obtain this equality. And this is nothing else than equations of motion of the Rusinard-Schneider system. If you write them in terms of time derivatives of coordinates, you get the equations of motion for trigonometric Rusinard-Schneider system. So this is the first part of the proof of that general statement about correspondence between Toda lattice and Rusinard-Schneider on the level of hierarchies. The idea of the proof is actually the same as that of the proof for rational Calogero-Moser system, which we followed in some details. But in this case, the idea is the same, but the technique necessary to apply this idea is much more complicated. And all calculations are much longer. Unfortunately, I don't know any other proof which would be simpler and more conceptual. Okay, so I will omit all these details. And consider now elliptic solutions. For elliptic solutions, we should do the same. Use this linear equation. But now this function v is expressed through Weierstrass function zeta function. So it is double periodic. Each zeta, when we shift argument by period, this zeta acquires some constant c, but this zeta acquires the same constant. So because of this minus sign, they cancel. So this combination is actually double periodic elliptic function of x with simple poles at the points xi and when x is equal to xi, and another group of poles is when x equals to xi minus eta. And the ansatz for a psi function should be taken in the following form. Here I will denote the spectral parameter as k. for the reason which will be more clear a bit later. And again, we need a Lamé-Hermite function. I remind you that it has the following form. So we have some coefficients, Ci, times this Lamé-Hermite function. So this is a double Bloch solution. Because the coefficient is double periodic, solutions to this equation should be found among double Bloch functions. And the convenient parameterization of a Bloch function with poles in n points is this. So everything here is much the same as we discussed before for other models. Now you should substitute these two formulas into the equation and cancel the poles again. So the result is the following. Now the L-Lux pair depends on additional parameter, lambda, spectral parameter, and we have the following conditions after cancellation of the poles. So we have time derivative of this vector, and it is obtained by applying matrix M to the vector C. And the explicit form of this matrices is as follows. This is diagonal part, and off diagonal part is as follows. And also there is an additional term but actually this term is irrelevant because it is just the matrix element ij of the Lux matrix. So when you write the Lux equation, it cancels because L commutes with this additional term. It disappears from the Lux equation, so it can be neglected. And the rest, in the rest, you can recognize the Lux pair for the elliptic Rosenow-Schneider system. Okay, now some words about the correspondence on the level of hierarchies. This result was obtained just 2 or 3 years ago, and it looks as follows. Consider the spectral curve. Spectral curve is obtained by from this equation in the form that characteristic polynomial is equal to 0. So it is equation for 2 variables, k lambda, and if they satisfy this equation, we have a point on the spectral curve. Now we introduce different spectral parameter. We express k through another spectral parameter z as follows. So the equation in the new variables, the equation of the spectral curve acquires the following form. A point on the spectral curve is a pair of z and lambda such that they satisfy this equation. From this equation, you can define a function lambda of z around infinity and expand it around infinity. And the coefficients in this series hk are exactly the Hamiltonians of the elliptic Rosenat-Schneider system. And they define evolution which corresponds to the flow, to the Toda flow with time k. There are 2 distinguished points in this curve. The first point is a point at infinity when z is equal to infinity and lambda is equal to 0. And the Hamiltonians which correspond to evolution with respect to positive times are obtained by expansion of this function around this point. But there is another distinguished point, P naught, which is given like this. And if you expand this function around the second point, around 0, when z tends to 0, then you get another expansion with some other coefficients. Already the expansion goes in positive powers of z. And these coefficients give Hamiltonians which correspond to evolution in negative times, in the times t bar k for the Toda chain. And they define evolution in the Kalodger-Moser system with the Hamiltonians which are obtained from these coefficients. It is not very explicit procedure because it is rather a complicated task to find them explicitly, express in terms of coordinates and momenta. Only H1 and H bar 1 can be found explicitly, easily, rather not very difficult task to find them explicitly, and they are just the Hamiltonians which we dealt with when discussed the elliptic Rosenau-Schneider system. Okay, now let me say some words about non-abelian Toda chain. The Toda hierarchy has an important generalization which is called matrix Toda lattice or non-abelian Toda lattice. It is a sub-hierarchy of multi-component Toda lattice. I will not discuss the hierarchy, the whole hierarchy, but concentrate on the first equation. And this first equation is written for a matrix G, invertible matrix of size n times n by n. And it is required to be invertible. This is important. And the equation of the non-abelian Toda hierarchy can be written in the following way. When n is equal to 1, you get a scalar, one component Toda chain, which we discussed before. And then in this case, if you parameterize it as exponent of some other function phi, this is when n equals to 1. Then for this phi, you get exactly the Toda lattice equation in the one component case. But here, the order of them, of different multipliers, is important because they are matrices, they don't commute. This equation was first suggested by Polyakov, but as far as I know, it was unpublished. Polyakov tried to find a difference analog of the principal chiral field. And this was his suggestion. Probably he introduced it even in the quantum case, when this entries of this matrix are non-commutative operators. But we will study elliptic solutions of this equation. And what we will get, you probably already know, that the result is spin generalization of the Ruijsenaars-Schneider system. To do this, we need to represent, excuse me, let me call it not n capital, but n small, because n capital is the number of particles. And here we have an extra integer parameter, which is the size of this matrix. And this equation can be obtained as compatibility condition for the following matrix linear system. Here, so you see that the first equation looks very much like the linear equation that we discussed some minutes ago, but there it was a scalar equation. Here, this equation is matrix. So psi is matrix of size n by n. And these coefficient functions, v and c, are also matrices. And they have the following form. It is a not very difficult exercise to show that when V and C have this form, then compatibility condition of this system is equivalent to this equation of motion. This is a problem for you. Now we should say what are these functions for these matrices for elliptic solutions. So we write them. Let me denote matrix indices by Greek letters to not to mix them with indices which number different particles. So the matrix element of this V matrix can be written in the following form. We have two vectors A and B. In scalar case, this was a constant, not constant, it was equal to velocity of ith particle. But now it is some dynamical variable, and using the constraint that scalar product of these vectors is equal to velocity of ith particle, you see that in the scalar case this equation becomes exactly what we had before. And C we don't need because it enters only the second equation, and we will substitute the ansatz into the first equation. And the ansatz for psi function can be taken in the following form. So it already becomes rather familiar. We substitute this and this into the first equation. And again obtain some elliptic function with poles at the points xi and xi minus eta. Simple poles, and you should cancel all residues, make them equal to 0 by choosing these coefficients Ci. I will not go into details of this calculation because it looks very much the same as we did before, and the result is the following, that this leads to the system of equations where the Lax matrix this is the Lax matrix, and M matrix is the following. Lambda I are some quantities which can be eliminated by the transformation which we already discussed on the example of spin Calogero-Moser model. It is some gauge transformation, and actually the coefficients are irrelevant. So you can recognize as this the Lax pair for spin generalization of the Rosenard-Schneider model. And this was the method how the system was first introduced. Unfortunately, the Hamiltonian structure of the system is not known. So we know only equations of motion, but whether they Hamiltonian or not is not known. This is still already maybe already 30 years this problem is open. The Hamiltonian structure of this system, if any, is not known. Okay, now let me say some words about Toda lattice of type B, which was introduced rather recently in our joint work with Krichyver, and it can be defined in the following way. So we should forget for a while about multi-component case and return to the one-component case and define the following operator. Phi of x is the field, Toda field, which enters the famous Toda lattice equations. And it can be, this phi is expressed through the tau function as follows. Let us impose some constraint on the Lax operators for the Toda chain. I remind you that they are series, in general, infinite series in the shift operator. Shift operator is this. It shifts the argument of any function by plus minus eta. So this one starts from positive, from the shift to the right, and all other terms are shifts to the left in some powers. And this one starts from shift to the left and goes as a series in positive shifts. And let us impose the following constraint. A problem for you is to prove that this constraint is preserved by flows of this form, but destroyed by flows with plus here. This means that we fix this combination equal to 0 for each k, and denote the difference as nu new times, and we can consider all functions as functions of these new variables with these combinations fixed. And they define a new hierarchy, which is just called B Toda hierarchy. It is a sub-hierarchy of the full Toda chain when all times are alive. We impose this, froze this combination of times and consider everything as functions of these times. And these flows preserve this constraint, so everything is okay in the definition. The definition makes sense. Let us obtain the first equation of the hierarchy. Consider the following difference operators. V, f naught, f1 are some functions. And consider the Zakharov-Shabbat equation for these operators. It leads to the following system. I denote the times as small letters, small t's. Or maybe, let me put this capital T's, this ones. So this is the system. The first equation, it is not a differential equation, and it allows us to express f1 as express it through the v function. Then it becomes identity, and we are left with two equations for for two functions, for f naught and v. You can also introduce Toda function by the following ansatz. This substitution makes the first equation an identity, so it holds identically. And the third equation can be represented as some differential difference equation for the tau function, which is bilinear. To find elliptic solutions, you should consider the first linear problem. But it is convenient to pass to a renormalized psi function. In terms of this capital psi, this equation acquires the following form. Where b is logarithmic derivative of the ratio of tau functions, and this function u minus can be also expressed through the tau function. Then the ansatz for elliptic solutions is, as usual, tau function is a product of sigma functions, and in this case, b is given by linear combination of zeta functions And this is elliptic double periodic again, because we have this zeta minus this zeta, and the additional term which it brings after shifts by periods cancel in this combination. And u minus and the ansatz for psi is, as usual, with some spectral parameter k. Now you should substitute everything into this equation, and again try to cancel all poles. And this gives the Lux pair, which I showed you before when we discussed the deformed Rosinat-Schneider system. Okay, I think it's enough for today. Next time we will probably discuss on the simplest example another method to obtain equations of motion of an integrable many-body system from nonlinear differential equations. This method was suggested by Krichever some time ago, and it consists in considering conditions when a linear differential equation has meromorphic solutions. They are not even required to be elliptic, just meromorphic. And this leads to, for example, in the simplest example, you consider a linear equation for KP hierarchy, the first one, which has the form of Schrödinger, non-stationary Schrödinger equation, and require existence of meromorphic solution, fix some point which is going to be a pole, and expand everything around this point, and the condition that the solution doesn't have any ramification or singularities of some other kind, only pole. So it is meromorphic, locally meromorphic. And this, if such poles, if there are several such poles, then you almost immediately get, from this condition, get equations of motion for the Calogero-Moser system. Probably this is the simplest way to obtain equations of motion. However, a drawback of this method is that it does not allow one to obtain any Lux pair for the system, for the systems which are obtained in this way. Okay.